Hello everyone. So today we're going to learn a little bit about types of immunological tests done in a microbiology lab, right? So immunological tests are those tests that detect antigen or antibody. So you can either detect an antigen that you do not know, or you can detect an antibody, right? So if you're detecting an antibody, the antigen is known, or you're detecting an unknown antigen, you already know the antibody, right? So detection of antigen or antibody is known as immunological test, right? So in microbiology we usually do it to detect diseases, right? Hepatitis, Neisseria, salmonella, right? A whole lot of diseases, right? Because these diseases, they have antigens, right? Hepatitis antigen, and then the body produces antibodies against these diseases, right? Hepatitis B surface antigen, hepatitis B surface antibody, right? So we can, if the person has the antigen or antibody, we can be sure that the person has the disease, right? And then we can treat the person. That's the logic behind all of it. So in for exams, the types of immunological test are agglutination test, Coombs test, precipitation test, complement fixation test, something called ELISA, radioimmunoassay, immunofluorescence, flow cytometry, and ICT, right? Uh, Among these, from examination point of view, and just to understand, agglutination test, precipitation test, complement fixation test, these and ELISA, these are the most important tests to understand, right? Other tests are also, I mean, important, but I mean, they're not that important, you know. So we'll just focus on these important ones. So agglutination test. What is agglutination test? Agglutination test is when there is agglutination happening. So agglutination basically means clumping together of RBCs. For example, this is a RBC, this is another RBC, right? If these two RBCs are now stuck together, like they're attached with each other, and then there's so many RBCs that are attached with each other like this, the RBCs now are clumped together, and then you can see the clumping of these RBCs in the slide. Like there's like, yep, so you've done the blood grouping, right? So when then RBCs, when some particulate things, solid substances are clumped together, that is known as agglutination, right? So here the antigen is on a solid particle. For example, the antigen that we're trying to detect is on a solid thing. For example, a cell. A cell is a solid substance, right? So if the antigen that we're detecting is on a solid substance, a particulate substance, we call it agglutination test. So the basic example is RBC blood grouping, right? So here, as you can see, there are a bunch of RBCs here, right? And they have this antigen. So for example, if the person, we want to know if this person has blood group A or not, right? So these are blood group A antigens, right? So we take a little bit of blood, put it on the slide, right? And then on the slides the RBCs look like this, right? On the slides the RBCs are like this. Now to this we add anti blood group A antibody, right? We add an antibody to this RBC, and this antibody is going to attach these RBCs. It's going to bind with these RBCs, and then it's going to make or agglutinate. It's going to clump these RBCs together. And when these RBCs are clumped together, previously these RBCs were far away, right? They were not attached with each other. When these are binded with antibody, they clump together and they form agglutination, and which you can see on the slide. So that is all about agglutination test. When the antigen is on a solid substance like RBC, we add an antibody. The antibody binds these RBCs together and it forms clumping of this RBC. If there is clumping, then the test is positive. If there is no clumping, then the test is not positive or negative. So we can do it on a slide, right? We can do it in a test tube as well. And then if you do it on, it's a tube agglutination test. Examples, important examples are blood grouping, Widal test for salmonella, Will Felix test for protease, right? So these are important examples that you need to remember. So the what I just described right now was direct agglutination test. Why direct? Because the antigen was already on the cell. But what if the antigen is not on the cell, right? If but it has to be on the cell to do agglutination. So if a antigen is not on the cell, then we have to make it on a cell, right? Or any solid particle. So if we take a antigen and then we attach it to a solid particle and then we do the same agglutination test, right? So we take an antigen which is not already on a solid particle, right? and then but then because it's not on a solid particle, we take it and then we add it to a solid particle. It could be RBC, it could be a latex particle or any other particle. We add it to a solid particle to make it a particulate or solid antigen. Non-solid antigen, add it to a solid particle, make it a particular antigen, and then do the agglutination test. This is known as indirect agglutination test, right? Examples are hepatitis B surface antigen antibody test, TPHA test for syphilis, right? Now let's go towards Coombs test. So Coombs test is nothing but a modification of agglutination test. So what is Coombs test? In this agglutination, what we were doing, we were adding antibodies to detect the antigens on the cell, right? But in Coombs test, we are not detecting antigens. We are detecting antigen antibody complexes, right? So RBC, this RBC already has this antigen. What we are trying to detect is we are trying to detect if this RBC has antigen or not. In order to detect it, an RBC with antigen is already there. So it is a antigen antibody complex, right? To this antigen antibody complex, we add a immunoglobulin. And after we add the immunoglobulin, this immunoglobulin, look, this is not binding with the RBC, it's binding with the antibody that is binded with the RBC. So this is binding with the yellow antibody is binding with the black antibody, right? So when we use antibodies to detect antigen antibody complex, we call that test Coombs test. So it's basically here also the agglutination is being formed. But what's the difference between Coombs test and agglutination test? In agglutination test, we were adding antibody to detect antigen on cells. Antigen, we're detecting antigen. But in Coombs test, we're adding antibody to detect antigen antibody complexes, right? So if antigen detection by adding antibody, agglutination, and comping agglutination. If antigen detection, antigen antibody detection by adding antibody, this is known as Coombs test, right? So, what is the example? It is done to check for the RBC diseases, right? For example, hemolytic anemia of newborn. So, in hemolytic anemia, it's an autoimmune disorder, autoimmune hemolytic anemia, in which the body produces antibodies against its own red blood cells, right? So, if a child is there and then we want to know whether the child has hemolytic anemia or not, the child's if the child has hemolytic anemia, the child's RBC should be bound should have anti RBCs, like anti RBC immunoglobulin with attached to them, right? Because the child is having the autoimmune disease. So we take a little bit of blood, and then in the blood of the child, the RBCs will be attached with anti the self-reacting immunoglobulin if a child has autoimmune hemolytic anemia. And then we add this anti-human immunoglobulin. So anti-human immunoglobulin is a type of immunoglobulin that binds with any it's a immunoglobulin that binds with immunoglobulin, right? Isn't that crazy? So it's a anti-human immunoglobulin is a immunoglobulin that binds with immunoglobulin. So if a child's RBC has this disease, hemolytic anemia, then the RBC will have antibodies, self-reacting antibodies, right? Because that's what happens in hemolytic anemia. And then if this is the case, if the patient has hemolytic anemia, and then after that to this antigen antibody complex, we add the anti-human immunoglobulin, it will start forming clumps. Then we can, and that is known as Coombs test, right? Then we can say that the child has hemolytic anemia, autoimmune hemolytic anemia. That's the basic principle of Coombs test, right? And again, Coombs test can be direct or indirect, right? Now, direct test is done to do this, right? If the antigen antibody complex is on a cell itself, right? But indirect Coombs test, right? It's kind of hard to explain here. Indirect Coombs test is done to detect antibodies that are not attached to the RBC. So, for example, the child has RBCs that have antibodies attached to them, right? But there might be some antibodies that can't find an RBC in the child's blood, self-reacting antibodies that are not attached with the RBC. So, in order to detect these self-reacting antibodies that are present in the child who has the hemolytic anemia, but they are not bound with RBC because they can't find any RBC. To detect free antibodies, we do something called indirect Coombs test. The scope of which I think we don't have the time to discuss that, but you get the basic idea about Coombs test, where we detect antigen antibody complexes. Now we come to precipitation test, the most important of these, right? In precipitation test, it is also very similar to agglutination test, but the only major difference is in agglutination test, we were detecting antigens on a particulate or solid particle such as RBC, antigen on RBC, which is solid. But if the antigen is soluble, not solid, it is soluble, it is dissolved, right? It is soluble, and we try to detect a soluble antigen, we do precipitation test. So the particulate solid antigen agglutination test, soluble antigen precipitation test, right? So what happens in precipitation test is again the same thing. So we take blood of a person, right? So in the blood, right, in the serum, let's say it's a serum, in the serum of a person, it has the antigens, right? So in order to detect if the person has this antigen or not, we add immunoglobulin or antibody to it, right? So here what we can see, there is antigen, there is immunoglobulin. Now this immunoglobulin will then react with this antigen. So previously the antigen was very small, it was soluble, right? It was in the serum, so it was dissolved, we can't see anything. It was like this clear area. Here in the topmost area there is antigens are there, the same thing, antigens are there, but we can't see it because it's soluble, right? In the bottom part the antibodies are there, but we can't see it because antibodies are also soluble. But when the antigen and antibodies they react with each other, what happens is again it forms lattices. Okay, so what happens is a single a single the antibody now binds with the antigen. So what this is, antibody has two binding sites, right? So one antigen is here, another antigen is here, and then this antibody, another antibody will bind two of these, right? So and then these antibodies will stick with each other, right? So when these antibodies are sticking with each other, they form a network of antigen antibody complexes, right? So this network is known as lattice, right? So they form a network. See, the antigen antibodies are reacting and they're forming a network. And when a soluble substance that was free, it was soluble because it was free, right? Now it's not soluble anymore because it is now binded with the antibodies. Then when a soluble substance becomes not soluble, we call it precipitate, right? So here the soluble, now the antigens and antibodies are binded and now it is forming a precipitation, right? Because it's not soluble anymore. So this is known as precipitate. So see here only on the middle part there is binding with antigen and antibody. So now this upper part was clear, right? Upper part was clear, the lower part was clear, but the middle part where the actual reaction is happening, when the lattices is forming, this is like a turbid, or this is where the precipitate happens. Now, so in this thing there is something called prozone phenomenon, right? That comes in exams. It's very simple. So pros in this test tube, in the topmost part there is only antigen, no antibody. So is there any antigen antibody complex happening? No, right? So that's why there is no reaction happening in the top part, right? In the bottom part the antibodies are there but there is no antigen, right? But we know that in order to form this precipitate we need antigen antibody complexes. So is there any antigen antibody complex happening in the bottom part where the antibodies are in excess? No, right? So that's why in this test tube you can see it's clear. But the area where the actual reaction is happening, for example the antigen and antibodies are in equal amount, right? That's why it's called zone of equivalence. I would say not equal, but in ideal amount, right? For example, for this sake of this example, if there were five antigens and there are five antibodies, it's a match, right? And only when there is a match, there is the antigen antibody complexes are being formed. And here you can see only on this zone of equivalence, the precipitation is being formed. So basic principle is if the antigen is in excess, right? No precipitation. If antibody is in excess at the bottom, no precipitation. But the precipitation only happens when antigen and antibodies are in equal amount. And that zone is known as zone of equivalence. And this zone where antibodies are excess, the antibodies are there but it can't find any antigen, this is known as post zone phenomenon, right? Post zone. And where the antigens are excess, right, still they can't find any antibody, still no reaction, this is known as no, this one is antibody is known as pre-zone phenomenon, right? And then antigen excess is known as post-zone phenomenon. I discussed this concept here, right? So when the antibody is more, it is known as pro-zone phenomenon, and when the antigen is excess, it is known as post-zone phenomenon. And when the actual reaction happens, whereas you can, as you saw in the test tube, the actual site of precipitation, this is known as equivalence zone, right? Zone of equivalence. So that is all about precipitation test, and you need to remember the examples, right? You can do the precipitation test in the test tube, as I saw. This is an example of soluble precipitation test. You can do it in a semi-solid media such as a agar as well, agar media as well. You can do it in the agar media, and then you can put this agar media in a electrical field, right? You do it in the electrical field where one side is positive, one side is negative. You don't need to know a lot about these, right? You just need to know the basic principle of precipitation test. So precipitation test, detection of soluble, dissolved, soluble antigens. Agglutination test, detection of particulate, solid antigens. For example, antigens on a RBC, right? That is that. Now let's go to something called complement fixation test, right? So complement, this is very interesting. So complement fixation test, what we do is we need to know certain things before we discuss this test. Okay, complements are a group of proteins in the plasma. Okay, they cause damage to the cells, right? When they are activated, they destroy cells. So they destroy harmful cells. For example, they destroy bacteria, right, when they are activated, but they can destroy other cells as well, like RBCs as well, right? So in this, what, and then we know that complements are activated by antigen antibody complex, right? So whenever an antigen binds with antibody, it activates the complement, and then the complement destroys the cell, right? So what we are doing in complement fixation test is we do complement fixation test for diseases that kala azar, filaria, neisseria, these diseases, right? So for, let's take an example. A person is having kala azar, right? And this, we need to diagnose for sure if he is having kala azar, not, right? So what we do is we take the blood of this person having this, with this disease, right, kala azar, and then what we add is we take the blood. So in the blood, the blood has kala azar antigen, right? It has cells having kala azar antigen, right? Because the person has the disease, so blood has kala azar antigen. So we put the blood, or rather the serum, or the antigen present in the blood, in the test tube, right? In the test tube, we put the blood in the test tube. Then to this blood we add anti kala azar antibody, right? So if the person has the disease, has the kala azar antigen, the antibody that we just added, it's going to bind with this antigen. What is it gonna form? It will form antigen antibody complex, right? And then after antigen complex, we add complement, right? Some complement proteins to the test tube, right? So if the antigen antibody complex is formed like this, for example, the antigen, this purple kala azar antigen, reacted with kala azar antibody that we added. Antigen in the patient's blood reacted with the antibodies that we added in the test tube, and then it formed the antigen antibody complex. Now what did I say? Antigen antibody complex now activate complements. After that, when we added complement, the complement got activated, right? But when the complement got activated, right, when the complement got activated, this complement is now binded with the antigen antibody complex, right? Right, now it is bounded, it is fixed. That's why it's called complement fixation test. Now this activated complement is binded with the antigen antibody complex. It can't go away from this antigen. It's fixed with the antigen antibody complex. After that, if we add sheep's blood or any RBC to this test tube, the RBC will not get destroyed, right? Because even though complement is there, right, even though we added the complement can't attack this RBC because it is already fixed with the antigen antibody complex, right? So if the RBC is not hemolyzed, then the test is positive. What do you mean by, if the test is positive, the person has kala azar antigen. When the person has kala azar antigen, it will form antigen antibody complex. When the antigen antibody complex is formed, then it will fix the complement, right? Because complements are now attracted to the antigen antibody complex. When the complement is fixed, after that, when we add the RBC, the RBC won't be destroyed because the complement is now not free, it is fixed. So the complement can't go and destroy the RBC. Now, in another, so that's the positive case. That is the positive complement fixation test. If the person has the disease, we get the positive complement fixation test, right? If the person, say, suppose the person did not have kala azar, right, but we took his blood now, and then we did the same thing, right? So if the person does not have this antigen, will the antigen antibody complex form? No, because the person does not have kala azar, right? So if the antigen antibody complex does not form, after this, if if there is no antigen antibody complex, will the complement will be fixed with the antigen antibody complex? No, because there is no antigen antibody complex, right? So the complement that we add after adding these two, right, after adding antibody to the person who does not have the disease, the complement will not be fixed. So when if the complement is not fixed, after that when we add the RBC, sheep's blood, right, the complement that is now not fixed is going to go and destroy this RBC. So if the person does not have the disease, he will not have the antigen. If he does not have the antigen, he will not make antigen antibody complex. If he does not make the antigen antibody complex, he will not fix, the complements will not get fixed with the antigen antibody complex. If the complements are not fixed with the antigen antibody complex, they are free to go and destroy the RBC. If the RBC is hemolyzed, then that is negative result. So positive complement fixation test, RBC is not hemolyzed. In negative complement fixation test, RBC is hemolyzed, right? So that is the basic concept for complement fixation test, right? Now we do this for these diseases, right? Just remember these names. Now ELISA, ELISA stands for enzyme linked immunosorbent assay, right? Enzyme linked immunosorbent assay. So what do we, it's a very common test, right, to detect antigens or antibodies, right? So I'm not going to go into the direct and indirect types because we don't have time. I'll just describe one of these types, right? So in ELISA, what is the name? It's called enzyme linked immunosorbent. So there is a immunoglobulin that is linked with a enzyme, right? So let's check. So in ELISA, for example, if for example ELISA, what is the disease that, okay, we use ELISA to detect HIV antigen, or say Kala Azar antibody. We'll say we are trying to detect HIV in a person, right? So if a person has HIV virus inside them, the body will make antibodies against the HIV virus, right? Now, if we can detect this antibody if the against the HIV virus in the person, then we can be sure that person has HIV. If the person does not have HIV, the person won't have anti-HIV antibody, right? Pretty simple concept. Now, in order to detect this antibody, anti-HIV antibody in that person, whether the person has anti-HIV antibody or not, right? What we do is there is kit, ELISA kit, right? It's basically like, I don't know, it's like a board, right, with wells in it, right? So there is, this is known as ELISA well, right? So in this well, it already has anti-HIV antigen already there. So we can, you can buy it in market, right? So this is the well containing anti-HIV antigen, right? To this, now we add the patient's serum to this well containing anti-HIV antigen, right? So if the person has antibody, anti-HIV antibody, this antibody is going to bind with this anti-HIV antigen that is already present in the well, right? After that, we add this immunoglobulin that is attached to this enzyme. See this immunoglobulin. So this is, so just to recap, we had a well that contains antigen, HIV antigen there, right? To this, we added patient serum. So if the patient has HIV, he will have anti-HIV antibody. So the HIV antibody will bind with the HIV antigen, forming a antigen and antigen antibody complex. Now then we will add another immunoglobulin that binds with this antigen antibody complex, right? Now this immunoglobulin, if you look closely, it has an enzyme that is attached with it, right? That's why it's called enzyme linked immunosorbent assay, right? So this is the enzyme, right? And we're gonna wash it. Now when we wash this thing, this immunoglobulin antigen it's not gonna be washed away, right? Because it is fixed. This thing is attached to this thing is attached to this thing, right? So even if you try to wash it away, it's not gonna wash away because this antigen is fixed with the bottom of the well, right? So it's not gonna be washed away. Now after that, so we have the antigen antibody complex, and then we have this immunoglobulin attached with enzyme that is attached to this antigen antibody complex, to this and this enzyme. So enzyme converts a substrate to a product, right? After that, we give a substrate, right? And what will this enzyme do that is attached to this antibody? It will convert this substrate into a product. And this product is going to be colorful, right? So in this example, down the product is colorful. So, so so if the product is colorful, if there is color change, right, then the person, then it LSI is positive. Then we know that the person has HIV, right? So if the person has HIV, the person will have anti-HIV antibody or HIV antibody, right? Right. So if the person has HIV antibody, when we add the person's serum or the blood containing antibody into this well, right, containing HIV antigen, it's gonna, the person's HIV antibody is gonna form antigen antibody complex in the well. To this, if we add the enzyme linked immunoglobulin, this is going to bind with this antigen antibody complex. When we wash it, it's not going to get washed away because it is fixed. This thing is fixed with this will, and then when we add the substrate, this enzyme that is attached to this, it's going to convert this substrate into a colorful substance, for example yellow color. So if the color is yellow, now if the color is yellow after doing the ELISA, you see it, if the color is yellow, or there is any other color change, if there is color change, then we know the person has HIV. If there is no color change, then the person does not have HIV. Why? Because if the person does not have HIV, he does not have HIV antibody. If he does not have HIV antibody, this antigen antibody complex will not form. If it does not form, there will be nothing for this to bind with. So if it does not form, then this thing will not have anything to bind because it binds with antigen antibody complex. And when we wash this immunoglobulin containing the enzyme that we gave, it's also going to get washed away, right? Because it is not fixed with anything. There is no antigen antibody complex formed. And then when we add the substrate, nothing is going to happen because there is no more, the enzyme is no longer there because it was washed away, right? So if there is no color change, then the ELISA is negative. That's how you can diagnose HIV by using ELISA, right? So that was, these are the most important ones. Apart from that, these are these tests, right? Flow cytometry and all of this. These are not as important. Just remember the examples, one examples. But I hope I tried to make these concepts clear, and I hope you understood something. I took a lot of time for me to understand it myself, right? So apart from this, there are some other terms that I'll link the note to this. I'll give a note to this, a link to this note. Okay. I'll leave a link to this note that I made in my website, which you can access it. It's called betternotes.framer.ai, right? So you can find this note in my website. Okay. So apart from this, there are other terms such as affinity, avidity. You can just read through this, and these are pretty self-explanatory. So, well, that's it for today's video. You can find all of this information in my website. I have lots of notes on pharmacology, microbiology, pathology, even community medicine, and even forensic medicines, right? So if you need any help regarding these concepts, you can always visit my website. That is that.